And we'll just say for the recording then, that just like in calculus 1, you had a domain, a set of all x you could input from a function, and a codomain, a set of all y values that you want to make possible, and maybe a bigger set than the y's that actually occurred. And then the range is all y's that actually occur. And so here y equals f of x is a curve in the xy plane when you have a function of one variable. Similarly, we'll get z equals f of x, y, a function of two variables, will create a surface over the domain that's a plane region, a set of x, y coordinates. And the codomain then will be whatever z's you're going to allow, but they don't all have to occur. The range is all the z values that actually do occur. So that's the idea of plotting in 3 dimensions. Oops. There's a loud noise outside. If it comes in here enough to bother you, let me know. They're cleaning the floor today. So this actually leads to some significant problems in here. The first one I'm going to make is pretty easy. Suppose f of x, y is the function that gives, if you put in x and y, it gives you x plus the cube root of x times y. And you want to find f of 1, 1. What is it? Well, it's just like function of one variable, you plug the numbers in. It's equal to 1 plus cube root of 1 times 1. Oh, it's just 1 plus 1 is 2, right? So you input the pair 1, 1, and you get out the number 2. So now you can do trickier things. You can find f of 2y squared for y. And when we write this, that means you replace x with this thing, whatever's in here, and you replace y with this thing, just like you did for functions of one variable. So this time we get x plus cube root of x times y, and I recommend just replacing x and y each in with parentheses. Then wherever you saw x, you put this in, 2y squared, and wherever you see y, you just put this in, 4y. So 4y goes in here, and here's the function f of 2y squared 4y. Whatever occurs here replaces x, whatever occurs here replaces y. And then we can simplify this, right? This is 2y squared plus the cube root of, let's see, 8y cubed. That reduces, so it's 2y squared plus 2y. You can write it like that, for instance. There's the idea of functions of more than one variable, just for basic calculations. And you can do functions of functions. Now, you can also do functions of 3 variables. So you can write w equals f of x, y, z. This is actually useful for density functions in the physical sciences, for instance, right? If you want w to be the density of the weight density or the mass density of an object at the point x, y, z in a solid, for instance, something like that, or maybe it's the strength of the electromagnetic field of the electric field, maybe at the point x, y, z. So you have those kind of calculations, a function of 3 variables. Now, this has domain in 3 space. And range real numbers. Your idea is you put in 3 real numbers and you get out 1. But we don't tend to sketch it. Right? Sketching requires 4 dimensions, so we won't do that. There is actually a really neat video online how to plot things in multiple dimensions, but it's not useful in practice. It's just sort of fun to watch. What I wanted to do now is talk about domains. There's something we call the natural domain of a function. If you define a function in terms of algebra and your standard functions and so forth, those things have certain restrictions for what you can put in, right? When you put a square root, you can't take a square root of a negative number, as long as you're doing real numbers anyway. If you put a logarithm, it's only defined for positive numbers, right? And those kind of things. If you put a division, you can't divide by 0. And so those kind of things occur. And we'll say sketch the natural domain, or the book will just say the domain, so I'll leave this off here. Sometimes there will be an explicit restriction in addition to the natural domain. But the idea is that when you have a function of two variables, you're sketching a plane region instead of an interval of numbers. So here's an example. Suppose I had f of xy equals the square root of x squared plus y squared minus 4. What is the domain of that one? There's a square root. What you do, here's how you work this. You look at for algebraic expressions, which means arithmetic, powers, and roots. That's what this is, right? Arithmetic, powers, and roots. You omit points where there's even roots of negative numbers. Or division by 0, or both. Everything else is well defined, right? You can add any two numbers, you can multiply any two numbers, you can take positive powers just fine, or odd roots just fine of both of any number. But you can't do division by 0 or even roots of negatives. So here, right, you can square any number, you can square any number, you can subtract any number. We don't have any problems, we don't have any divisions, except we have one even root, we have a square root. So we simply say the domain is all xy such that this isn't negative, right? But whatever the argument of the square root is, isn't negative. So we'll say, is this greater than or equal to 0? Now we see what it is, right? It's equivalently, I write these double arrows, this means if and only if, or equivalently, meaning has the same solution set. So the same solution set as by adding 4 to each side, x squared plus y squared greater than or equal to 4. Well, what does that look like? We can sketch that, right? What you think about is what's the boundary of this plane region. The boundary is if you put equality. Boundary is x squared plus y squared equals 4. Oh, that's a circle of radius 2, right? X squared plus y squared equals 2 squared is a circle at the origin, radius 2. So here's the sketch then. And there's sort of a tacitly assumed principle going on here that they don't tell you about. If this is a continuous function, well, they can't tell you about it yet because they haven't said what a continuous function of two variables is, right? We know continuity for a function of one variable, but we haven't defined it for two. So they don't say it yet, but the idea is if you have an algebraic expression like that, then it's continuous, as long as you don't get a division by 0 or even root of a negative. And continuous functions have this property that they don't jump suddenly to where they're like here. Since this is a continuous function of x and y, as it turns out, it can't jump suddenly from being less than 4 to being greater than 4. It has to go continuously through it. So you sketch the boundary here, the circle of radius 2. And then all the points inside are either in the domain or all not in the domain, and all the points outside are either in the domain or not in the domain, because it's a continuous function, right? This is continuous. It doesn't suddenly jump over 4 from being positive to negative without going through the boundary. So that's what we'll do. We'll sketch the boundary, and then we'll just check a point inside, like 0, 0. 0 squared plus, now look at the inequality. Do I still have it up here, I hope? I think, yeah. If I put in 0 for x and 0 for y, oh, it's not greater than or equal to 4. So that's not in the domain. The origin isn't. I deduced that all the points in here are not in the domain. Now I try a point outside, whatever it is, say at 3, 0. 3 squared plus 0 squared is greater than or equal to 4. So this point is in the domain. It follows, because the function is continuous over here, that all points out here are in the domain. So we sketch this region here and say this is the domain of this function. So you can write that this is the domain. If you want to write set builder notation, you write it in a fancy way and say set of all x, y. The bar means such that x squared plus y squared, I should draw from this one, shouldn't I, is greater than or equal to 4. That's the domain written in set builder notation. But I kind of like to sketch these. It gives you a lot better feel. It's all points on or outside the circle of radius 2 with the origin. So this is a sketch answer. One thing that comes up in here that you have to be careful about, you only draw this curve that's the boundary solid if it's included in the domain. If it's not in the domain, then you draw it dotted. Here, equals 4 is in the domain, right? You want x squared plus y squared greater than or equal to 4. So you include the circle as well as the points outside. And you draw a solid circle and shade the outside region. So there's sketching the domain for this function. I'm going to see how far this camera goes over. It's about to here. It's hard to tell sometimes. All right. Let's try one more on that. These are kind of tricky. But it gives the idea simply that a function of 2 variables, the domain is now a plane region instead of an interval of the x-axis. It still outputs a real number. You sketch it as a surface in 3 dimensions over the domain. And when you sketch the domain, what you can do is just find the boundary and check each side when you're dealing with continuous functions. This one is actually a homework problem here. Let's see where to go. There we go. Example, sketch the domain of this function. ln of 1 minus x squared minus y squared. Actually, I'm going to change it. 1 minus x squared. I'll let you do the one that's on there. If I put z equals ln of 1 minus x squared, but I'm thinking of this as a function of 2 variables, then I still have to plot it in 3 space, right? If this is a function of 2 variables and y can be anything, and you still get this rule for z, we'll sketch it in 3 dimensions. So what do we sketch? Or what do we sketch for the domain? The domain, you first find the boundary, right? What's the boundary? Once again, this part in here is an algebraic expression. We just have to omit even roots of negatives and divisions by 0 where there aren't any of them. But then I have the ln function. Ln is only defined for its argument greater than 0. So what I want the domain of the boundary is u strictly greater than 0, since you can't take logarithm of 0 or anything negative. Equivalently, that is 1 minus x squared greater than 0, which is equivalently, well, you can factor it like this. 1 minus x times 1 plus x has to be greater than 0. By factoring now, you notice that the boundary, I'm sorry, this is the domain. The boundary is where this is equal to 0. And so the boundary consists of the 2 lines, x equals 1 and x equals minus 1. That makes this equal 0, right? Now you can check on each side of those lines and see what's in the domain and what's not, since this function here is continuous. I just have to check between the lines and on each side of the line. So the line x equals 1 is a vertical line like this. The line x equals minus 1 is a vertical line like this. There's 1 and minus 1 marked on the axis or something. Minus 1, 1. And now I just check between. I put in 0. 1 minus 0 is 1. Times 1 plus 0 is 1. 1 times 1 is greater than 0. So the 0 point, 0, 0, is in the domain. I'm going to shade all these points in between the two lines. Now I check a point out here anywhere I want. Say 2, 0. Let's see. 1 minus 2 is negative 1. Times 1 plus 2 is 3. Negative 1 times 3 is negative 3. That's not greater than 0. So all these points over here, it follows, are not in the domain. Now I'll try this point over here. Minus 2, 0. 1 minus a minus 2 is 3. Times 1 plus minus 2 is minus 1. Again, I get minus 3. That's not greater than 0. So this point is not in the domain. Neither are any of these. This is the domain right here. And what I've done is I've properly sketched it because I don't want to include equals 0 in here. I make the boundary dotted. So here's the sketch for this one. This is the domain here. If you want to call it A or something. Is between these two vertical lines. But that's what you have to do for the homework, is be able to sketch these plane regions from the equations that you get out of looking at what avoids arguments that are, for which a function isn't defined, and an algebraic expression avoid even roots of negatives and division by 0. Again, we can do a last example here. I don't want to do too many. Do all your homework problems already, probably. But I'll do one similar to the other homework problem, not the same one. Suppose I want to find the domain of f of x, y equals 1 over x minus xy. What's the domain of this function? Well, you look at it and you say, this is only an algebraic expression. I don't have to worry about where's a function, a sine, a tangent, or a log, or something undefined. I just have to say, no, there's no roots. I don't have to worry about those. I only have to worry about a division by 0. So the domain is all the points where u is not equal to 0, right? The denominator. Equivalently, that is x minus xy not equal to 0, which is x times 1 minus y not equal to 0. And this is where this means x is not equal to 0, and at the same time, so we'll put or, and so x can't be 0, and y can't be 1. So it's this plane region. You omit the y-axis. That's x equals 0. You omit the line y equals 1. And everywhere else you shade. So the domain is everywhere but those two dotted lines. They're sketching domains.
Excuse me, I have a question.
Yeah.
Okay, for the last question, you said that -2 and 0 are not in the domain. But then when you plug it into the equation, like the 1 minus x and 1 plus x, it gives you 3. And that's more than 0. No, for the -2 and 0.
For 2 and 0.
No, the other one,
This
-2.
one, minus 2.
Yeah.
Yeah, 1 minus a minus 2 is 3. Times 1 plus minus 2 is minus 1. I get minus 3. Minus 1 times 3 is negative, and so this point's not in the domain.
Oh, okay. I was using 0 as.
It's tricky because it's got lots of minuses in it. I always have trouble with the questions that are not, you tell your mom, it's not the case I'm not going to the movie. It's kind of throws her for a loop, right? That's what happens in some of these problems. All right. Let's try actually sketching some of these functions. We said we want to not just sketch the domain, we want to sketch the function itself of 2 variables. And again, we won't sketch function of 3 variables because we have to draw in 4 dimensions, but we can actually sketch level surfaces of them later, so that will be useful. And kind of get an idea, just like you can draw those level curves, the contours for the isoplus of the mountain that we talked about, you can similarly draw level surfaces for functions of 3 variables later. So here's a good example for sketching graph. Sketch, this time, the graph of the function. So this is going to be a surface over the given domain. Z equals square root of 4 minus x squared minus y squared. I introduced this one because there's one little trick in here you want to be able to do. How do you figure out how to sketch that? Just have confidence is half the problem, actually. They don't give you these unless it's something you've already learned how to sketch. They're not going to give you some exotic curve that you have to go to MATLAB to plot, right? So you think, how can I sketch this? This is equivalently by squaring both sides. Z squared equals 4 minus x squared minus y squared. Well, that's not quite equivalent yet. What's wrong? This radical means the non-negative number that has this square, right? So I have to first, I have to additionally restrict this to z greater than or equal to 0. Right? So now they're equivalent because this gives me the non-negative number whose square is this, just like this did. So that'll be equivalent. Now, how do I sketch that? Maybe the object is to rework it into something you've seen before. If you add x squared and y squared over here, it's all just algebra. You get x squared plus y squared plus z squared equals 4. What's that an equation for? Let me give you one more suggestive hint here. What does that look like? X squared plus y squared plus z squared equals r squared is
A sphere.
Yeah, sphere in 3 dimensions, right? Just like x squared plus y squared equals 2 squared is a circle in the plane. This is a sphere in 3 dimensions at the origin. So you go ahead and sketch that, except I want to carry down this restriction that z has to be non-negative, so it's actually going to be a hemisphere when I include the restriction. A half sphere. So I'll draw it like that. The half of the sphere that has non-negative z coordinates. So it goes out to 2 on the y-axis, 2 on the x-axis, and up to 2 on the z-axis. There's the sketch of the function itself. But sometimes you have to do those tricks. Use some algebra to rework it. And when you square both sides, make sure you put in the restriction that the original variable can't be negative. Okay, now another one. How about this one? Sketch the graph of z equals x squared minus y squared. What's that? Oh, and I maybe should have put here, when you think about it, there is actually a domain problem for this. This can't be negative. So the domain is where this is greater than or equal to 0. It's the region in the xy plane, 4 minus x squared minus y squared, bigger than or equal to 0, which is, I hope I didn't move the camera over too far, maybe I did. So the domain is only this region, which is x squared plus y squared less than or equal to 4. It's the interior of the circle of unit 2, of radius 2 in the xy plane. So if you sketch it here, this is the domain in the xy plane of that region. And as you can see, I sketched it that way anyway, but it is sometimes useful to sketch the domain so you know. So the red lines are not part of the sketch of the function. I'm just sketching the domain with it. All right. Now let's sketch this other one. This one has no even roots or divisions by 0. So I'm going to sketch it for all x and y. What is it though? The trick is to go back and recognize this has the form of something you've seen before. Just like the sphere does, right? This is z equals x squared over a squared minus y squared over b squared. What is that called? One of the hardest ones, actually. This was a hyperbolic paraboloid. In calculus 3. If you think about it, remember how you can figure out the name? You can try holding one of the variables constant, like put y equals 0, and you get z equals x squared over a squared, a parabola in the xz plane. If you put x equals 0, then in the yz plane, you get z equals minus y squared over b squared as a parabola down in the yz plane. And if you put z equal a constant like 1, you can get x squared over a squared minus y squared over b squared equals 1, a hyperbola. If your cross sections are parabolas and hyperbolas, you use the duck rule, I call it. You say, well, it waddles like a duck and it quacks like a duck. It must be a duck, right? So if its cross sections are parabolas and hyperbolas, it must be a hyperbolic parabola. Right? So we can sketch this, and especially when we recognize here a squared is 1, a is 1 and b is 1. You can sketch some cross sections if you want. I don't want you to be real accurate. You can let software do that some other time. But for now, just get the idea. What is it? It's a hyperbolic parabola. How do I sketch it? In the xz plane, I sketch parabolas upward. In the yz plane, I sketch parabolas downward because there's a negative here. And let's see, yz plane, parabolas downward. So it looks like this. And then in the xz plane, it looks like this, and it comes down through the origin, right? If you put y equals 0 in the xz plane, you get z equals x squared over a squared. It's a parabola through the origin. And it's like this. Remember, the hyperbolic parabola is actually the hardest one. It's a saddle. And so it has hyperbolic cross sections in this direction. There's the hyperbola. Parabola is down, parabola is up. So it looks something like that. And I don't care if you put in the numbers on this one so much, but if you put in those 3 cross sections that I call them traces in the book, then you can draw this with more accuracy. Like if you put y equals 0, this is the curve z equals x squared. So you can put in some specific points, 0, 0, 0, 0, 1, 1, and minus 1, 1 in the xz plane with y equals 0. Maybe this is minus 1, 0, 1 here, and this is on the parabola z equals x squared. This might be the point 1, 0, 1. And this would be the point 0, 0, 0. I don't expect you to draw those points, but you can kind of see that you could, is the idea. But that's the idea of that part, and I'm going to do one more here. Put it far to the left, I guess. Sometimes it's not one of those graphs. Here's what you have to look for when you do these sketches of functions of more than one variable. Look for spheres. Look for quadratic surfaces. Most of these are either spheres, quadratic surfaces, or they can get planes, or they can get cylinders. And so this is the hint. These are the things I'd like you to be able to draw for tests and so forth. I'm giving homework problems kind of like that. Here's another example. Suppose I ask you to sketch this one. Z equals 2x plus y minus 1. What is that? Immediately by looking at it. Well, you rewrite it in this form. Minus 2x minus y plus z You know, now that I think about it, that could be in this semester, but I think it was last semester. Let me double check before I finish this example.
Is that just a plane?
It's a plane, but I wasn't sure if you saw that all of a sudden in Calculus 3. We do planes this semester, but in the sense of tangent planes. Did you see planes last semester? I can't remember. But it's a plane, yeah. Here's the thing. In the plane, any equation of the form ax plus by equals c is a line in the plane, right? We learned this. This is the general form of an equation for a line. Whenever a and b aren't both 0, this is a line, and every line can be given this form. So we call it the general form of a line in the plane. Similarly, if you have an ax plus by plus cz equals d, this is the general form for an equation for a plane as long as a, b, and c aren't all 0. At least one of them. Two of them can be 0. And so every plane can be put in this form, and every equation in this form is a plane. I recognize immediately when this is a linear function equal to number, ax plus by plus cz equal to number, it's a plane. All I have to do is sketch 3 points not on a line and put a plane through them. Just like here, to sketch the line, you plot 2 points and put down your straight edge. Here you plot 3 points, put down your plane. So we could do it that way. We could say, well, if x and y are 0, then z equals -1. So we put this point, 0, 0, -1. If y and z are 0, then x equals 1/2. So I can put this one, 1/2, 0, 0. It's easiest to sketch them on the coordinate lines, and you can sketch it accurately, right? If you want to plot 1, 2, 3, it's kind of hard to, right? You have to draw that rectangular blocks and stuff. And then if x and z are 0, then you get y equals 1. So it goes through these 3 points, and I just have to draw sort of a triangle like this, and I'll say there's the plane right there, or if you like, you can draw a big thing that looks like a plane, but it's hard to see it as well. We'll say this is the plane that goes off to infinity, but it contains that triangle. There's what you get if you get z equals a linear function. It always just comes out to be a plane. And finally, you do see some of these in there. Can't remember if that one was there now, but I want to make sure I presented it. Suppose I put z equal y squared plus 1, saying this is actually a function of x and y in 3 space. You put in x and y, and you get out y squared plus 1 always, right? But I have to draw in 3 space, not just in the yz plane. So what do? I plot in the yz plane z equals y squared plus 1. Oh, it's an easy parabola, right? Because I know how to plot y equals z squared. It's just in the plane of the board. There's z equals y squared. Goes through these points 1, 1, 0, 0, -1, 1, and so forth. And then z equals y squared plus 1 just moves that up 1, right? It makes every z coordinate 1 greater. So it's exactly the same shape, shifted 1 unit up. This is one thing you learn this semester too, is how to do great graphs a lot of things. Here is z equals y squared plus 1. Just shift that parabola up 1 in the plane. So you get, for instance, this point, 0, 0, 1, right? In 3 space. And now what happens with x arbitrary, you just slide this, we say we extrude it in the x direction, and we make a parabolic trough called a parabolic cylinder, right? So it looks like that. It's like that. Every cross section is the same parabola. So there's sketching in 3 dimensions. If one of the variables is missing, then it's a cylinder. You just slide it in the 3rd dimension. And that covers pretty much all the cases they're going to throw at you. I'm gonna throw it to you. There are also some domains for functions of 3 variables. Then you have the domain as a region in 3 space. So suppose we say find the domain of the function f of x, y, z equals x, y, z over x plus y plus z. What's the domain of that function? Since it's a function of 3 variables, I have to draw in 3-dimensional space. And since it's an algebraic expression, I only have to worry about even roots and divisions by 0. All I need is the set of all denominators not equal to 0, right? So this is equivalently x plus y plus z not equal to 0. But what's that? Not equal to 0. If it was equal to 0, it would be a plane. So we have all but the plane ax plus by plus cz 1x plus 1y plus 1z equals 0. When the right side's 0, it's a plane through the origin, right? Because 0, 0, 0 is a solution. So it's a plane through the origin, and we're going to find out this semester that actually is perpendicular to the vector with components 1, 1, 1. But if you plot a few points just like you did there, what you'll see is you got a plane that looks kind of like this. And it's perpendicular to the vector that comes out here with 1, 1, 1. Some of these are kind of hard to draw, but there it is, an x, y, z space drawn with right-handed coordinates. The plane here, if I draw that with dotted lines, means leave out the plane, then the domain is the rest of 3-dimensional space. So let's say it's all 3-dimensional space except for this white plane here, x plus y plus z equals 0. That pretty well covers the first section, 13.1. And guess what we want to do once we learn about functions of 3 variables? Of course, it's calculus class. We want to do calculus with them now, right? So this has kind of a neat interpretation. In calculus 1, you start doing limits because limits allow you to define asymptotes, and then they allow you to find derivatives, and then they allow you to find integrals. You have to do limits first. So we want to do limits of functions of more than one variable. Z equals f of x, y.
Sir, it's 8:35.
Yeah, we go to 8:45, right?
Yeah.
Oh, never mind then.
Yeah.
Okay. Yeah, 7:30, 8:45. Unfortunately, we have long classes. I really prefer the 50-minute classes. I think everybody sleeps the last 25 minutes. I probably put you to sleep as well. All right. So limits of z of x equals f of x, y. We want to do something really analogous to what we did in calculus 1 for limits of a function of one variable, but the picture is a whole lot different. And so we'll say this definition applies. You want to see the definition so you know when it's true. I took a bunch of physics class. I was interested in applying mathematics to physics as a mathematics PhD, but I took classes in physics to be able to do something fun with it. And I was very disappointed. I go over there. I never knew when I could apply the formulas. They tell you these formulas, and when does it work? You couldn't tell. So I was glad as a math major I could figure all this stuff out. Let's see what the rigorous definition of limit is for that reason. So go and take your physics class or engineering class or chemistry, whatever you take. You can figure out whether it applies or not. Definition, if for each epsilon greater than 0, there exists a number delta greater than 0. Remember the epsilon delta definition from calculus 1 maybe? Such that if absolute value of L minus f of x, y is less than epsilon, then, oops, I'm sorry, what is less than, I wrote this backwards. If square root of x minus x0 squared plus y minus y0 squared is less than delta, then it follows that absolute value of L minus f of x, y is less than epsilon, then we say that the limit as the ordered pair xy approaches the ordered pair x naught y naught of f of xy is equal to the number L. That's the definition. If you've understood that, you're a better mathematician than I was. What is that, right? I mean, it looks terrible. The thing to do, let's see if I can zoom this out a little bit. I think I need some more room. Oops. Hope you can still see that. Maybe I'll zoom it a little. Doesn't that look familiar? In calculus, when we saw this one, this analogy for a function of one variable, we said if for each epsilon greater than 0, there exists a delta greater than 0 such that if absolute value of x minus x naught is less than delta, then absolute value of L minus f of x is less than epsilon. Does that look familiar? I hope. Sometimes they skip this in class. This is the rigorous definition to say that the limit as x approaches x0 of f of x is L. And it had this really nice interpretation. I mean, to me, this is just great intuition that Leibniz came up with to be able to do this. I want to say that a curve, as you get closer and closer to x0, here's y equals f of x, is getting closer and closer to this point. It kind of looks like it. L, y equals L. Here's y and here's x. So for a function of one variable, you're thinking of this. How do I say that it has that limit? Maybe it's not even defined at that point. We're just saying it gets closer and closer on the sides. How do we make that rigorous? We do this. We say, you tell me any number epsilon, any positive number epsilon, and I'll make an interval of width 2 epsilon. I'll make epsilon on this side, and I'll make an interval with epsilon on this side, and I'll make a band of width 2 epsilon. And the idea is, if you say I have to be within epsilon of this number L, I can find a region, no matter how small, as long as it's a positive length, say this one right here, from x0 plus delta to x0 minus delta, such that each point on the curve is in the band, then I've satisfied this criterion for your epsilon, right? If I pick x within this band, so that the distance from x0 is less than delta, this interval, if I pick x out of this interval, then the y value will be within epsilon of L, right? You say, well, that was too easy. I made epsilon too big. I'm going to pick a smaller one. Now you pick epsilon down here. Now squeeze it in there. Well, what I do is I go, let's see. Here's the point I'm trying to get. I go over and I say, well, now it's a band only this wide, but I can still do it, right? I just pick this little piece of the function. And I say, well, that corresponds to x0 minus delta here and x0 plus delta here. And if no matter how small you pick your interval, some positive interval with, I can find a corresponding positive interval width here that squeezes that piece of the function that close, then it gets squeezed arbitrarily close by simply choosing a small enough interval, then we say the limit is L. It's getting closer and closer to L as we squeeze the interval smaller and smaller. That was the definition in calculus 1. So what did we do over here that's similar? We just did a function of two variables. Now we're saying in x, y, z space, we have some point x naught, y naught, or x0, y0. And this equal to a fixed number is a disk, right? If you put this equal to number and square both sides, you get a disk of radius delta. Right? The interior of a circle is called a disk. Disk, radius, delta at the point x0, y0. And so I have to find a small enough disk like that, of radius delta, such that for your given epsilon, I can squeeze the surface up above. And maybe this is my proposed limit L. It looks like it's getting closer and closer to that number. And if I take the portion of the surface up here over my disk, it'll be at squeeze between your L plus epsilon and L minus epsilon. So will you give me an epsilon? Now it gives me two planes, a plane epsilon unit above L and a plane epsilon units below L. And I try and find a piece of the surface that fits between those two planes. And if I can find a disk of any positive radius delta that squeezes a piece of the surface between those planes, then I've satisfied your criterion. You said you make delta smaller, I just squeeze my planes closer and make a smaller disk, and now it squeezes between. And the idea is, if I can always do this, find a disk small enough that I squeeze between your two planes, then I say that the limit is L, and there's the definition for limits of functions of two variables. Well, with that, I probably about used up my time. So we won't get to do any examples. We really need a little more thinking to do some examples. But keep this one in mind. This is the next section, 13.2. And we'll do some calculus next time. I just wanted you to see this formal definition. I'm not actually going to ask you to prove anything with this, so don't worry about it. But this is partly why you come to class. You need this later for higher dimensions and other things. This is just a beautiful thought experiment. How can you make this rigorous? This is how you prove limits for functions of two variables and analogy to functions of one variable. Thank you for your attendance tonight. Let me leave you some homework problems here. If I can find where I put them now. There we go. Please try these. Again, these are not to turn in if you came in late. These are practice for the test. All the test questions will be like these that come from this section. 1, 3, and I'm going to skip all the way to 23, 25, 27. This is just full of problems, this section. 33 to 43 odd. And 51 and 53. And they'll be doing a lot of the things we did tonight. Sketch the domain, sketch the function, plug in different things for the variables and functions of more than one variable, and those kind of things. And then we'll continue with limits next time. Thank you for your attendance. Bring questions on these next time. That's what will help me to explain this better.
Do we upload the assignments on D2L, or we just like do them for practice?
Just do the homework, but don't turn it in, because it's practice for the test. I'll upload what I recorded out of the lecture in case you missed parts. I know some people have technical difficulties tonight. I'm sorry it's so awkward to do this. Come see me on office hours at the same address. Just click on it on your PDF. It'll take you right to my office hours during my office hour times.
Professor, do you mind upload the homework problem?
I'm sorry, that was distorted. Say again.
I mean, do you mind upload the homework problem to D2L?
Oh, do I upload them? No, I just write them on the board. That'll make you come to class.
Do you mind like scan the page and then upload? Because I don't have the
Oh, you
textbook.
want to scan the page? You don't have the book?
Yeah.
I can probably do that if you send me an email. Yeah.
All right.
Send
Thank
me
you
an
so
email and
much.
Scan the pages for a while. Yeah. Thank you. Have a good night, everybody.
Have a good night.